So let's go on with the public talk. So the public talk will be about artificial intelligence. This is a subject that raised in popularity the last 2-3 years, as everybody knows. It can be used, well, for various reasons. One is smart Googling. The other is big data analysis, in medicine, various other sciences, experiments in high energy physics, banking. Could be used to manipulate people in elections or what to buy. But what about theoretical physics? In our subjects, we are driven by curiosity. We don't care immediately what we find to find applications. So the question is, does artificial intelligence has a place in theoretical physics? And the question here is it just to do things faster, or can help people, scientists, to make easier, let's say, conceptual advances? That's the question. So the person to tackle this problem in this workshop, how do I proceed with the transparency?
Wait, you can.
Okay. So that's the last one, don't worry. So the person to talk about the subject is Vasilis Niarchos. So let me tell you a few things about his career path. He finished our university, the University of Athens, in 1998. Then, as it was at the time the habit, the best students go and do a PhD in the US. So Vasilis went to the University of Chicago, where he got his PhD in 2004. Then he did a series of postdocs in very good places like Niels Bohr Institute in Denmark, École Polytechnique in Paris, then where he had some Marie Curie fellowship, and then for quite a few years in the University of Crete as a senior researcher. That was not enough to get him a permanent job there, so he went for a few years to the University of Durham, and then he returned back in the University of Crete in 2019 as an associate professor. Very recently was promoted to professor, and his research topics, as you might have already an idea from his talk, and his from Inspires and elsewhere, is on string theory, QFT, and gravity, and in particular intersection between these three topics. And the reason he's giving this talk today is because in the last few years he implements methods of artificial intelligence in tackling problems in non-perturbative quantum field theory. Okay, so Vasily, the floor is yours.
Thank you very much, Costa. So let me change the slides. Oops, what happened? Okay, very good. Thank you for the introduction. It's a pleasure to give this general public talk, especially because it's in my alma mater. So I want to, Kostas set it up very nicely. So basically, I will not go into a lot of technical details. I will mainly try to discuss general concepts around AI and possibly whether some of the techniques that are being developed there are useful for us. So it's basically mostly an exhibition of examples and concepts through examples from our field, and you will be the judge whether this is something useful for you. Okay, so let me start from Wall Street, not from AI or physics. You all have heard about DeepSeek a few months ago. This paper here on the right appeared on the archive at the end of January this year. And this is what happened when the markets opened the next day. basically all the tech stocks in Wall Street sharply dropped, especially NVIDIA, which makes all these fancy GPUs, chips that people use to train AI models. And as you can see from, this is basically a photocopy from the Wall Street Journal website. You see DeepSeek undercuts belief that chip-hungry US players will win AI race. But what's really amazing to me is like a paper from the archive really has this huge immediate impact. Now, we'll come back later on this DeepSeek paper to discuss, some of its aspects, but I want you to sort of pay attention a little bit to the following aspects here. First of all, I won't read the abstract, but some things to keep in mind is that basically what these guys are trying to do is try to find a cheaper way to train these large language models, and in particular what they're trying to achieve is higher reasoning capabilities for their models. And what really scared the market is the fact that they were able to do it in a much cheaper way than, for example, OpenAI that has ChatGPT. Another thing that another term that appears here is reinforcement learning that we will encounter later on. Also, another thing that I want you to pay attention to is, like, for example, well, two things. One thing is that unlike OpenAI, they open sourced their code, so everybody can play with it. They can download it on their computer, which is a major difference. Another thing is that here they say that they give you some relatively small models, distilled models, and the number of parameters is of the order of a few billion. If you ask ChatGPT how many parameters ChatGPT 4 has, it will say about 1.7 trillion parameters. Okay? And you can see it's really competitive on reasoning tasks. Okay, so let me drop this. So obviously there is a lot of impact of AI on commercial applications, but already the previous slide hints on the fact that people are also interested, for various reasons, on reasoning capability, right? And this is very important for us as scientists, because a useful tool for us will be a tool that can actually think. And here is an abstract from another paper that appeared in August last year. I will read the abstract here. Basically, I like the abstract because it has all the words I would like to say. And it gives a sense of what people are thinking about. Like it says, one of the grand challenges of artificial general intelligence, AGI, is developing agents capable of conducting scientific research and discovering new knowledge. While frontier models are the foundation models like ChatGPT, have already been used as aids to human scientists, for example, for brainstorming ideas, writing code, or prediction tasks. They still conduct only a small part of the scientific process. This paper presents the first comprehensive framework for fully automatic scientific discovery, enabling frontier large language models to perform research independently and communicate their findings. We introduce the AI scientist, which generates novel research ideas, writes code, executes experiments, visualizes the results, describes its findings by writing a full scientific paper, and then runs a simulated review process for evaluation. Okay? Now, I read the paper. It's an interesting idea, but it gives you a sense of what people are trying to achieve. It is indeed somewhat effective in, say, computer science, not the most complicated task, obviously, or the most complicated paper in computer science, but I find it very hard to believe how it will be able to do this kind of process in our field. Okay? It looks impossible. Okay, so before I go on, I would like to make a distinction between two kinds of things. Like when one sort of thinks about the topic and says, okay, I have this set of methods, new methods, what would I like to achieve? Well, the more traditional approach that you can take is that, well, look, we have been using machines forever in science, right? Like since the abacus, when we were counting numbers in the ancient times. So this is not new. Now we have a new set of tools, and they perform all sorts of different tasks, and we can use them to supplement what we're already doing with computers, like computational tasks. For example, it could supplement things that we're already doing with Mathematica. Okay, so you can view AI or ML methods as a new toolbox for novel computational techniques, and basically today's focus will mostly be this one. So I will go through basic techniques or categories of machine learning methods, and I will give you examples in some examples, by far not a complete list of what has been done in our field, but some examples that tell you what kind of things you can do. Okay. But a more radical approach is one where, and it is hinted by the previous slides, is one where AI and human intellect basically share the driver's seat. So in the first approach, where we command the game. Basically, we set the problem, we're thinking about the problem, we generate the ideas, and then we end up, I don't know, with some set of equations that we want to solve, and it's a practical problem. But here, it's much more impressive. So what if you had algorithms that are great at reasoning, that they can brainstorm and give you new ideas, you can collaborate with them, and maybe even solve some problem. And usually here people have in mind large language models, like ChatGPT, for example. It is quite likely that real breakthroughs in science are going to come from this direction, but this is still much under development. Good. So in this talk, again, I don't want to approach the subject from the point of view of computer science. Really what I'm interested in is how I can use all these new methods to say something new or make some progress in problems that I care about in theoretical physics. Now we can ask more generally, can AI be useful in physics in general? The answer is immediately obvious, an obvious yes. There are many areas of experimental or observational physics and more generally physical sciences that are using AI methods or machine learning methods very actively already for many years now. Experimental high energy is of course a great example. People from chemistry, I don't know, materials, biology, medicine, basically wherever you have to deal with big data and you have to find patterns, whatever, AI has been a great tool. But can AI be useful in theoretical physics? It's not so obvious. In fact, like none of our talks, for example, used any of these methods, right? And most of the tools we're using are not really very good for the kinds of problems that we want to solve. So the number of AI applications in this area is less widespread. That's obvious if you compare with other areas. So what I want to do is go through some examples from quantum mechanics, quantum field theory, and mathematics to see if there are some potential gains that we can make by incorporating some of these tools in our toolbox. Now, before I do that, I want to ask, in some sense, I want to ask, is theoretical physics hard for AI? I mean, why has it been so hard for us to apply these methods? And I will, again, use a phrase from the DeepSeek paper that says, this phase focuses on enhancing the model's reasoning capabilities, particularly in reasoning-intensive tasks, such as coding, mathematics, science, and logic reasoning. All of this stuff are stuff that are of interest for us, which involve well-defined problems with clear solutions. So basically, I really need to bring the problem at the stage, essentially at the final stage, and then this method will solve it. Okay? So many of the most interesting problems in what we do are faced with both conceptual and computational problems. It's not just conceptual. And in other areas, they have a very clear computational problem that they have to solve. There are lots of data, so this is all data-driven, and then it's easy to use these methods. Moreover, many of our problems, and I think it's evident from many of the talks we had so far, involve structures that go beyond, first of all, they involve structures that are typically not finite dimensional, they're infinite dimensional, so it's typically hard to put them on a computer, okay? And also, traditionally, in our field, sometimes we have to go beyond the mathematical structures that are already available. Like in theoretical physics, generated new mathematics along the way, okay? So there is also another difficulty in applying these methods. Theoretical physics, as I already said, is typically not data-driven. Okay, it's not like astrophysics or whatever, or chemistry or material science. We play a lot with concepts, and we do not have this aspect. And moreover, a lot of what we do requires rigor and interpretability, but ML methods are usually stochastic, error-prone, and black box. So even if they give some result, we want to be able to trust the result, and that is not obvious. Okay? So the question here is, how does one extract reliable analytic information from typically statistical methods? That's one of the reasons, basically, why typically we don't use such methods. We're not accustomed to using such methods. So I want to give an example. The example is extreme, okay? But I want to highlight it as an example where really it's nothing, because there's nothing conventional about this example, okay? So, two of the big problems in our field, the problems that drive really our field, is how to make sense of quantum gravity, how to put together, we have two excellent frameworks, classical gravity and quantum mechanics. We want to put them together as a framework of quantum gravity. And this has been driving a lot of our efforts, okay? Another very difficult problem is, well, we know how to do quantum field theory to some degree, but not really quantum field theory non-perturbatively. Again, a lot of talks encountered this problem. And string theory, which is an even more complicated encompassing framework, came out of this effort to solve these problems. So it provides a more general framework where some of these answers can be understood, and this framework itself is very poorly understood because it's very, very complicated. In particular, as an example, string theory predicts an exotic QFT in 5+1 dimensions that everybody here knows. It is called the 6D 2,0 theory. It has no tunable coupling. It is inherently strongly interacting. And more importantly, it's one of these examples that doesn't have any Lagrangian description. Right? The first thing we learn about in first years in university is you give me a Lagrangian or a Hamiltonian, and I know what to do after that. This is the basis of mechanics, is everything. Okay, but this one doesn't seem to fit in this framework. I like to mention these examples in front of my condensed matter colleagues who have a shock. They cannot think that it's possible to do anything without a Hamiltonian. So standard non-perturbative QFT methods, like non-perturbative means beyond perturbation theory, we don't have a lot. One of them is lattice field theory, and we will not have been able to apply this here because there is no Lagrangian. Okay? So again, what am I trying to say here? I'm trying to say that we, in our efforts to understand better the frameworks that have already been proven as very valuable frameworks in physics, through a long sequence of logical arguments, we're led to a more complicated structure, and we're really lost how to navigate through the structure. Okay, and it's really a conceptual problem. It's not simply a computational problem. So it doesn't fit nicely into this, basically these kinds of problems that involve well-defined problems with clear solutions. Okay? Good. So having said this, okay, let me now try to propose 3 ways in which we could try to use existing ML methods or artificial intelligence methods to advance some of the problems that we're thinking about. Well, the first one is to try to use these methods to efficiently manipulate and learn infinite dimensional structures. For example, all sorts of kinds of functions, okay, that appear in our problems with deep learning methods. And here a key word is representation learning. Representation learning is crucial, is a big deal in computer science. How you extract, important information from a complicated structure, for example. Another thing that we might want to do is to learn how to transfer knowledge from accessible corners of the theory to inaccessible corners. And, as I will mention later on, there are many situations where, we have a quantum field theory or whatever, some quantum system or some other physical system. We understand part of the story in some easily accessible corner, but then it's very hard to really understand the full story. Can we transfer knowledge from what we understand to the more complicated general picture? Another thing we can do is try to discover new solution strategies. We're solving problems, so maybe we can find some new ways of solving them. And again, the point I'm trying to emphasize here is what I'm trying to propose is not that AI is some magic box that's going to come and magically solve all the problems that we have. Clearly not. But I think that there's going to be a lot of fun and potentially a lot of gain if we use them alongside methods we have already developed, or analytical understanding we have already developed to take the next step. And that's precisely what I'm trying to emphasize here, that all of these directions, if we can implement them in any successful way, they will require the clever incorporation of domain knowledge, okay, stuff that we're already doing, okay. So what's the plan of the talk? The plan of the talk is really simple. I want to take these 3 points and illustrate relevant techniques and set up some language from deep learning, basically, for those that are not familiar with it, through examples and applications in theoretical physics, basically quantum field theory, and one example from mathematics. Okay, so let me set up some language first. When I talk, first of all, machine learning means a set of a lot of methods. Some of them involve neural networks, other methods do not involve neural networks. Usually when we talk about AI, we have in mind things that involve neural networks. So neural networks are going to be important for us. And so the point is that neural networks are a particular way to model functions, okay? So usually you will see this picture. There is input 1, 2, 3, 4, 5, n, whatever, and then there is a number of outputs, and you see all these neurons. They're connected like this, and they remind a little bit the human brain or whatever. But the concept is really, really simple, right? It's basically how do you represent a function. Now, we know many ways of how to represent the function. I don't know, you do some Fourier analysis or whatever. This is another way to do it. And it's really elementary. What you do is, suppose that X is the space, your domain, the vector from the domain of the function. So this is the input. You take it, you act with an affine transformation. So basically, you do linear transformations and you add a shift. Then you pass it element-wise through a nonlinear function that usually it's some simple nonlinear function, like tan h, for example. And then you repeat this many times. So every layer here is essentially one of these steps. So it's a composition of affine transformations composed with a nonlinear function. Very simple, okay? And there are universal approximation theorems that tell you that if you take the width to be sufficiently large, then you can approximate any function with some assumptions, general assumptions, within some error. Notice that by doing this representation, I managed to represent the function in terms of a number of parameters. The parameters are basically these WMNs, which are constants, and these BNs. I will collectively call them as a vector. I will denote them with a vector theta. Okay. So when I was saying that, for example, in the abstract of DeepSeek, that there is a model that has 70 billion parameters, I'm referring to these types of parameters. Okay. Now, there are some other keywords here. For example, what does it mean to train a neural network? Again, the concept is very simple. You want the function to have some properties. For example, you want it to have specific values, or you want it to satisfy some equation. Okay? The idea is to tune your parameters theta so that your function fits the criteria that you want it to satisfy. And typically, this involves solving a complicated non-convex optimization problem. And this is typically hard and rather costly. So if you have a model with 1 trillion parameters, obviously you're optimizing in some 1 trillion parameter space with some landscape that is very complicated. That can be a really costly operation. But that's all we mean. So basically, training means fitting. Find the parameters that reproduce the function that you like. There is also another thing called hyperparameters. When you do the training, you can do the training in all sorts of different ways. I don't know, like use different optimization algorithms, use different learning rates. You know, there are all sorts of parameters that are not optimized during this process. Okay. but you're free to choose them in some particular way. And sometimes you choose them in some way and optimization works great. Other times you choose it in another way, the optimization doesn't work at all. So scanning over hyperparameters to find the optimal hyperparameters is not an easy task. It is also a costly business. Another word is architecture. What I showed you here is the simplest feed-forward neural network architecture. So everything is fully connected, just go forward. But you can imagine other kinds of architectures, and different architectures could be better for different problems. So there are different kinds of algorithms of type of neural networks that are good for achieving different things. For example, for I don't know, like for pictures, you want something which is known as a convolutional neural network. Okay, or for sequences, you have other kinds of neural networks. A popular architecture for language, for large language models, in fact, the main algorithm that is in ChatGPT, in models like ChatGPT, is something called transformer. Here's a quick picture of how the transformer looks like. It still contains stuff like this, but it also has other built-in features. Now, there is another thing that you can also do. So far I was emphasizing the fact that we can use neural networks to model functions, okay? But another thing that you can do, which I think is really cool, is you can also model operators, so maps between infinite dimensional spaces of functions. For example, suppose that you need to solve an initial value problem and you give some initial condition with some specific function, you solve your differential equation, at later time you have another function, the time-evolved function. Instead of solving the function, it would be nice to know the map that takes you from the original, the initial value function to the final function automatically. Like in quantum mechanics is the time evolution operator that does that. Okay? So it is possible to learn operators using neural networks, okay? And this is one way, for example, to solve complicated differential equations, like, for example, Navier-Stokes equations, okay? And I will give some examples later on of this. So during training for a neural network, what you do is you have, I don't know, 1,000 samples of X, you pass them, okay, and you say these are 1,000 outputs, and you try to fit things with a ground truth, for example. Here, instead of passing points, I pass whole functions. I pass function 1, function 2, function 3, etc., and I get, I don't know, 1,000 different functions as output. And try to learn the weights and biases, all these parameters of a more complicated architecture that will fit basically this map, okay, between the functions that are input and the functions that are coming out. So this is called the neural operator. So now let me go through these 3 points and try to illustrate examples, applications of these algorithms. So the first one, remember again, the first one was efficiently manipulate and learn infinite dimensional structures. As an example, here I will focus on learning functions by solving equations. Pretty standard thing. And this will also give us example of what is called unsupervised learning. So the idea is that we can use neural networks to find an alternative to standard numerical methods for systems of equations. And these equations can be very general. They can be systems of algebraic equations, they can be systems of PDEs, integral equations, whatever. Okay, so the idea, the name of the approach here is called PIN. It's called physics-informed neural networks, because basically you try to fit a function that satisfies an equation. For a computer scientist, an equation that comes from physics already tells you that this is a physics-informed neural network. Okay, although you could use it for other purposes. So what's the idea here? Pretty simple. You want to solve for a function. Neural networks give you a way to approximate functions. So you say, I will model the function as a neural network. And then I will try to put the equation as a loss function. Tells me basically what is the error. So, you know, I have some weights. I produce some function. I plug it into my equation and see how bad is it. Okay? Then I try to manipulate all these weights so that I bring the loss function down, and hopefully achieving to great accuracy essentially loss close to 0. Okay, then I have satisfied, I have found a neuromorphic approximation of the function that satisfies the equation that I want to find. And this is what training means. It means find all these weights and biases, all these parameters that give you a neural network that minimizes the loss. Obviously, it's an optimization problem. Okay? And if your neural network has, I don't know, like 3 million parameters, then you have to optimize in a 3 million dimensional space. Okay? Now, the nice thing and the thing that has actually given a lot of impetus in the last few years is that people realize that stochastic methods like stochastic gradient descent can efficiently solve such problems. So you put it on a computer and stochastic gradient descent, for example, which is a typical optimization method that people use, works pretty well. So instead of giving you an example here from some standard PDE, let's say Navier-Stokes equation, let me give you an example motivated by quantum mechanics. I mentioned this example also in our first cost meeting, but I want to repeat it. You'll see why it's a nice exhibition result. It has some features that, I don't know, solutions, for example, of PDEs do not have. Okay. So what's the problem here? So here, this is an aside on quantum mechanics. So suppose that I do, again, I go back to standard quantum mechanics from an undergraduate course, and I do scattering in 1 or 3 dimensions. 3 dimensions, for example, is more interesting, where I have a target modeled by some potential, and then I send in some incoming wave, it scatters, and then it gives them, with some probability, I observe a beam in this direction, that direction, etc. So one way to solve this problem is to solve Schrödinger's equation, time-independent Schrödinger's equations, and find the eigenstates of the energy that represent the scattering process. And the large distance asymptotic form of the wave function is what we call the scattering amplitude. Okay, it's part of the wave function, so you square it, you find probability. That probability basically tells you what is the probability to see the particle here, there, okay? Which is more carefully phrased as a differential cross-section. So this is a basic relation in quantum mechanics scattering. Differential cross-section is equal to the scattering amplitude squared. Now, the scattering amplitude, as I said, is part of the wave function, so it's a complex function. It has a modulus and a phase. But when I do the experiment and I collect data from different angles, right, I get information only from the modulus, not from the phase. So I cannot directly reconstruct the whole wave function. Now, why would I like to know the whole wave function? For example, if I go at very high energies and work to leading order in a perturbative expansion, if I know the full wave function, I can Fourier transform it and get information about the potential that does the scattering. Okay? So you want to ask if you can reconstruct the phase of the scattering amplitude from information that you get from the scattering experiment on the modulus B of z. And there are several ways to try to attack this problem. First of all, you know, when I solve Schrödinger's equation in 3 dimensions, one way to do it is do an expansion in spherical harmonics, right? And since I assume here azimuthal symmetry, it's basically an expansion in Legendre polynomials. Z for me is cosine theta. Theta is one of the spherical coordinate angles. And this is a formula that you know very well. Basically, I can express the scattering amplitude as an expansion in these polynomials with some coefficient, and there are some real parameters that appear there that we call phase shifts. So if this is a finite sum, then a finite number of such parameters completely characterizes both the modulus and the phase, the full wave function, the full scattering amplitude. Okay? So as a human, for example, this is easy for me to understand, right? You have 10, 11, whatever, 1,000 parameters. It's a finite number. I know the function. Okay? It's easy to play with this. But typically, the scattering amplitude is not going to be a finite sum. It's going to be a sum involving a whole series. So now I have to deal with an infinite dimensional, something that has an infinite number of parameters. So people asked this question in the 60s and 70s, and it was studied by various well-known people like Martin, Atkinson, and others. And the key to understand the relation between modulus and phase is unitarity. basically the fact that not all probability is always 1 in quantum mechanics. So then, there is an argument that you can make, which you can find in Landau-Lifshitz, tells you that the phase phi and the modulus b, here I multiplied with the momentum, the actual phase, so I call this capital B. So these two functions, I have two functions now of basically z, which is cosine theta, and they are related by this integral equation. Okay, so all my ingenuity led me to this equation. Now I have to solve this equation. So the game here is you give me B, because I read it from the experiment, and then I tell you, I solve this equation, I tell you what phi is. Okay, and I reconstruct the wave function. Notice that this equation, okay, it's not the most complicated equation you have ever seen, but it's also not the simplest one. For example, here you see I integrate over z1 and phi 1. z2 depends both on z, which is the external parameter, z1 and phi 1 in this particular way here. Okay. So now you can ask, can I give you any b and you will get a phi? And the answer is no. For example, if we said z equals 1, which is an external parameter, here you see if I said z equals 1, this goes away. This becomes 1, so z2 equals z1. But when z2 is equal to z1, this is cosine of 0, so it's 1. And therefore, I get just an integral of the input function, b. So this thing is going to be sine of some angle. And it better be less or equal than 1. So if you give me an input function b, whose integral, this integral, is greater than 1, I won't be able to solve that equation. Okay? So this is an example where, like there are, sometimes you get a solution, sometimes you don't get a solution. Okay? So it makes the problem, later the problem of solving it, or if you want, the ML way of solving it more interesting. Secondly, there are additional bounds on existence and uniqueness that can be obtained by defining this function, where basically it's the same integral, but I just dropped the cosine. And then I can look at this k of z, look at all the values that I get I scan over all the values for all possible values of z, and I get the largest number, and I call that largest number Martin parameter. Okay? Now, formally, it is denoted here as sine of mu. It is denoted like this because you can argue when this number is less or equal than 1, just like a true sine, okay, then you can argue that you can always construct a unique solution. Okay? But if it's greater than 1, solutions may or may not exist. They can, if they exist, they can be unique or doubly ambiguous. Okay? And to this day, people don't really know what is the general story. Okay? When ambiguous solutions appear or whatever. So recently, Darcy, Swartz, and Ziboedov wrote a paper where they used a pin.
This mu is could be complex.
Yeah, exactly. Or sine mu is not a good name for it. Okay, so think of sine mu as a formal way of characterizing this parameter. Okay, I didn't even have to use sine there. Okay, so these people used a pin to solve the above unitarity equation with remarkable results, including the discovery of a new ambiguous solution with the lowest known Martin parameter, around 1.67, which was essentially the world record, the new world record after 50 years. Because people were looking what is, the ambiguous solutions with the lowest possible sine mu. And there were some results, so this was basically the new world record. Okay, so how did they do this? Again, the idea is very simple. You're looking for a function, okay? Model it by a neural network, characterized by some parameters theta, and then formulate a loss function, which is basically your error. So you compute, say, this equation is the left-hand side minus the right-hand side. You evaluate it at a number of points. So you discretized your z values. So say you take 100 values, you evaluate essentially your error in 100 points, you square this, you sum and average, and basically you're trying to tune all these parameters theta so that this becomes very small. That's the game. Okay, so that it's very simple. And then you minimize with respect to these parameters, theta. And these are some plots of what they got. For example, if they scan, again, you have the possibility of scanning all sorts of different functions, right? So, but they scanned here as an exhibition on linear functions, B, and quadratic ones that you can easily argue do not have a finite partial wave expansion. And red is basically no-go regions. They are not finding solutions there that have low error, okay? This gray curve is the curve that is set by the exclusion bound, this one. So everything outside it should be red. It should not be possible to find a solution there. Indeed, the pin doesn't find any solutions there. Inside, it's not clear, okay? But you know that you should find solutions inside this I, which is bounded by sign mu equals 1. So sign mu less than 1, we know from theory that there should be solutions. Indeed, they find solutions there, okay? It's more complicated when it's quadratic, okay? There they find these solutions are spurious. They just numerically close to some finite partial wave solutions, but they shouldn't really be there. These two ones, these two little islands here, are solutions that should be there. They're in fact L equals 2 solutions. Okay, so this is an example of unsupervised learning. Why? So why do we call it unsupervised? Because in this particular case, we do not need to prepare beforehand a set of data, experimental data, if you want, that will guide the search. Okay, so the algorithm generates its own data and does and optimizes.
So
yes.
In the previous transparency, what is at the end admissible is the common area, the common blue area.
The blue area. The blue area is the admissible one.
If I keep going with different polynomials, should I shrink it more and more?
It changes. It's still an I, but it depends on, you know, I mean, I've gone up to cubic order, for example. It's very similar. Okay.
So you're going to ask something?
Yes.
I'm trying to understand what exactly was done here. It's an optimization problem.
Yes, that's right.
But why don't you optimize your original function, you know, just parameter it any way you want and optimize that?
You can do that. The point is to find an expressive enough parameterization that will allow you to approximate the function you want to approximate. But up to this point, that's why I'm trying to say it's very, very general.
Yeah, exactly.
Exactly. The new element is that I have now a generic way and a generic expressive way to represent functions through a neural network representation. That's it, right? You see, it's very simple, and I'm trying to present it as very, very, very simple.
It's not as if, you know, I made it think or whatever, just optimize something.
Exactly. Well, the optimization may not be practically easy, right, and wouldn't have been possible a few years back. It's possible now in modern computers, right? But the idea is very old. Right. Even with this representation is old. It goes back to the 90s. It's just that they didn't have the computers to put it on a computer. Okay, that's it. So it's very simple conceptually. Good. So you might have heard of other applications in our field of basically the same method. Like all these applications with numerical Calabi-Yau metrics are morally in the same class. Okay, as they're solving the Einstein equations. Okay, they're looking for Calabi-Yau metrics. Of course, they're using a lot of domain knowledge to, you know, they don't take the raw Einstein equations. They make all sorts of ansatz. They use, I don't know, like supersymmetry, whatever, write things appropriately. A lot of domain knowledge goes into this, and then they parameterize things with neural networks. Okay, but again, morally speaking, it's not something complicated. Okay. But the thing I want you to appreciate, and maybe will be useful for you practically, is, you know, it is a way to manipulate functions. Okay. So now let me up the game a little bit and ask the following question. What happens when the model is unknown? Like we don't know this equation, for example, right? Or we don't know, I don't know, like the Lagrangian or whatever. And there are only a few experimental data available about the structure we want to uncover. Then what do we do in that case? So usually this involves information restricted in some corner of parameter space. So we could think of ourselves as experimentalists of the mathematical world, and we can ask, can we identify new structures and learn the model from the available observations? Can we transfer what we learned from a restricted corner to the inaccessible, the hardly accessible regimes, generating new predictions and or conjectures? So this is point 2 of part 2 of the talk. Okay, so how do I take information, restricted information from a corner, and sort of like generalize it somewhere else where I cannot do any calculation with traditional methods? That is much more interesting. Okay, and to bring it into context, so suppose that you performed a nice complicated computation in a weakly interacting quantum theory, quantum field theory, for example. Can we learn something about the non-perturbative properties for the theory? It's not clear that we can do it, but in some cases it might be possible to do it. You know, sometimes, I don't know, like for example, we discover some structure like topological and topological relations or whatever in some supersymmetric theory, and we find that the data we want to compute satisfy they have some hidden structure. Maybe these methods can discover the structure and then can generalize it into a non-perturbative regime. That's what I have in mind. Or we did an exact analytic computation using special properties. We used symmetry or supersymmetry, for example, or integrability. We had a lot of nice talks about integrability in this workshop that allowed us to compute a set of semi-protected data. Can we use this information to learn something about the generic unprotected observable? That's really what motivates me in this subject. So let me go to point 2 and keep going with the same example. Okay, so now what I want to do is take the same example, but I want to remove basically the human input. I want to remove the fact that we know this integral equation that relates the modulus with the phase. Okay, so what do I want to use? I want to use only the fact that if I have a finite partial wave expansion, I can easily generate consistent scattering amplitudes. Because it's a finite sum, I plug in whatever phase shift that I like, and I get a function. Okay? And that gives me examples of consistent functions. It's called consistent scattering amplitudes, but nowhere in there have I input a complicated relation like this one. The question is whether I can discover it just from this very limited data in the easy corner, which is finite partial wave expansion. So can we learn the map, the operator between the infinite dimensional spaces of modulus functions b of z and phases phi of z, or when a phase does not exist, just from the data of finite partial wave expansions? That's what I want to ask. And this is what we tried to do with Kostis Papageorgakis in a recent paper. So we trained a neural operator on 300,000 true b phi samples, just basically generate randomly phase shifts, and rid of B5s on a cluster with one of the NVIDIA chips. And then we produce an operator that once you give it a B, you do it only once, by the way, the training. Previously, in the pin case, you gave me B, I have to do an optimization problem, I tell you what phi is. You give me another B, I have to redo everything from scratch. Okay? Here, I do the training only once. I give it 3,000 different functions, and it learns how to make predictions on generic B. Okay? And so we have now this neural operator. It's trained on finite partial wave expansions, and we ask it to make predictions on infinite partial wave expansions. Okay? How well does it do? Well, here I have to stop, right? I cannot do anything really. I mean, I have the prediction, but really I cannot do anything with it. Why? Because I don't have any way to test the prediction, right? I removed that equation, the unitarity equation, so I can make a prediction, but how do I test it? It could be garbage. I don't know, right? It will make predictions even when there's not supposed to be a solution. Okay? And that is a generic difficulty in this game. It's not enough to train, right? Reliability, being able to say with certainty that, what I found is correct, is super important. Okay? Now, for a moment, give me the ability to bring back that equation, okay, and make a similar plot like the Darcy et al. Plot. You see, it makes pretty good predictions. So it was trained. Okay, so for these linear profiles, the losses are down a bit higher than the pin results, but it can actually generalize. Okay, so it's now making predictions that are basically correct in a case that it hasn't seen before, which means it has learned that equation, that complicated equation, simply from finite partial wave expansions. Okay, good. But let's go back. Okay, let's
go back. What is this curve between which connects the eye to the?
This one.
Yeah.
Yeah. This is like there. It's not super accurate. It seems to be seeing something here. Okay.
So before you knew that anything outside should not be there.
Yes.
This is consistent with the red color.
Right.
Now
it's not super accurate. Right. It's ballpark correct. Okay. But obviously, I'm not doing the super intensive like work that I was doing before, because now I'm generalizing on a case where it hasn't seen before. I think what we need to take from this is that with these assumptions, it didn't do such a bad job. Okay?
Can I do a question, sorry?
Yes.
Could we do an intermediate step and give the information about the concept of unitarity without the unitarity equation?
I have given it, indirectly, I have given the information about unitarity by using the fact that the phase shifts are real. Okay, this is where the information is. Okay, but it has to recognize that and then generalize in a situation where there are an infinite number of phase shifts. That's a non-trivial thing.
So the information about unitarity is there?
It's there, right. It's there, but it has to recover it in a more general context. Yeah. So, so this is the generic difficulty. So what did we do next with Kostis? We said, okay, we need to understand this. Okay, so let's do the following thing. I mean, we have been showing it through examples. We have been telling it what is a correct B-phi pair. Okay, but we haven't told the machine what it means to make a bad prediction. So it just makes predictions and things, all are on equal footing. Okay. So to address this problem, we retrained the neural operator, exposing it to 225,000 true pairs, just like before, and 175,000 false pairs. Right? So here we generate, basically we take, the B's and the Phi's are completely random. Okay? And at the same time, we supply the neural network with an extra label, a classifying label, that tells it, this pair is correct, this pair is wrong. This pair is correct, this pair is wrong. Okay? So in that sense, we run a simultaneous classifying regression task. Okay? Regression is find the function, classification is it correct, is it not correct. Okay?
Sorry, but binary or almost correct? So it's correct?
No, here during training is 0 or 1. Okay? Obviously, when it makes predictions now, it will spit out a label, and that label is going to be some number. It doesn't even have to be between 0 and 1. This is how we set it up. So it could be some number. Okay? Now, we would hope that B very close to this parameter F close to 1 means that it thinks that it's a correct solution. I should trust it. So now I have a new function defined in terms of weights that I would have never imagined defining on my own by trying to understand the problem, okay, that potentially has something to do with the unitarity equation. Okay? So, and again, I find this quite out of the box. Okay? So here I'm plotting again on the right-hand side what I had before from the more accurate Darcy et al. Plots. On the left, basically I'm plotting this F. So now the colors are inverted. So red means it's allowed, blue is disallowed. Okay? Now what I take out from this is that very sharply distinguishes allowed and not disallowed and makes islands of allowed regions. Again, just like with the bootstrap, it gives me a disallowed region. And the disallowed region is basically always correct. Okay? So not only that, what really surprised us is that, look, before here,
how do you know that it converges to a certain state at the end?
Well, again, all of this is, rarely there is some analytical understanding behind this. As always, computer science people, you know, they do the experiment. So we do the experiment, this is what we observe, and that's what I report. Okay? Indeed, I would like to know more than that. But notice here, when I did this plot, these two blobs of allowed solutions were not there. I couldn't see them, right? When I do it, when it uses its own criterion to say, is there a solution here or not, it finds these two islands, and they are precisely where Dersey and all found it. So merely the fact that it was trained also knowing bad solutions, it has a better understanding of the equation. Okay? Yes. So let me give another example. Again, this was a quantum mechanics example. Again, a scattering amplitude example. As you know very well, in quantum field theory, we're interested in, you know, this is where we do scattering experiments for QCD or whatever, and we can really solve the theory at weak coupling, so we organize things in a perturbative expansion. Higher orders means more loops, more computational complexity, so although this is an analytical method, it's not exact. You do one loop, you do two loops, after a number of loops, you're dead. Okay? So people have been thinking hard in this business how to make more efficient calculations, like don't compute directly the integrals, okay? Try to understand what the answer is, and try to bootstrap the answer, okay? So in recent years, much progress has been achieved in high loop computations in planar n equals 4 per Yang-Mills theory, and the idea is bootstrap the answer by studying the space of functions where the amplitude lives and the relations it must obey. I find this an extremely nice idea, this whole bootstrap idea, and you know how it could be married with this kinds of methods is also one of the driving forces in what I want to do eventually. So many amplitudes can be expressed in this game as linear combinations of generalized polylogarithms, basically integrals of rational functions. The final answer is obtained by solving a large number of linear relations, which becomes challenging around 9 loops, basically because you get lots, exponentially large number of terms. So people have distilled all the information that appears here in terms of polylogarithms in some symbolic language, in terms of a symbol. These L's that are called words are basically functions of the external momenta, Lorentz invariant combinations of the external momenta. You put them together in some particular way that reminds a word, because you put letters together, you make a word, and you have to make a sentence, so you have to sum them with some coefficients that are integers. Okay? And if you know this symbol, then you can reconstruct the amplitude. Okay? But the number of elements in a symbol can be very large. For example, they look at a 3 gluon form factor, and it goes like 10 to the 12 at loop at 8 loops. But they can but in this language, you can formulate it. You can view it as a sequence to sequence task. Basically, it looks like language, so you can formulate it as a language task. And that's what they did. So in this paper, it involves Lance Dixon, involves people from Meta, etc. Notice in computer science, not in heptates. Okay? They use transformers with a few million of parameters to learn the sequences for a certain class of amplitudes in n equals 4 per Yang-Mills theory. And they made predictions of prediction of simple coefficients where you train, say part of the L equals 4 data seems to be an easy task. So it reproduces all the rest with very high accuracy, like 99.9%. Then you can ask, does it learn all these linear relations, complicated linear relations? The answer is yes. They can see that it learns this as it trains. A more interesting thing, which again brings me back to what I wanted to achieve before, like generalize, go to where you cannot go, is whether there are any cross-loop relations. So for example, and the first baby step on that is basically if you train, suppose that you're interested in L equals 6 predictions, loop 6 predictions, but you also train it not only on L equals 6, you also give it the full L equals 5. Does it do better in L equals 6 tasks? And they see evidence that it does. Okay? And their whole program, which is not finished yet, is basically to use this algorithm to make now predictions at higher loop levels, okay, where it's not possible to go with traditional techniques. So So what's the summary? In part one, we encountered examples of unsupervised learning. The algorithm generates its own data and trains to identify structures. Part two, we encountered examples of supervised learning. Here we have to provide labeled data, and then it trains on those data. In the next and final part, in a few minutes, I will discuss another type of learning where one learns how to act. Okay? And I think that might be the bridge with the less traditional approach where the AI comes in as an equal partner and helps us in reasoning tasks. So this is part three, discovering new solution trust strategies, and this come under the name of reinforcement learning. So the idea here is basically it's the task that a robot has to do. So we're really discussing robots here, okay? So robots are inside some environment characterized by some states. They have to take some actions, okay? This is the action space. And then when they do something, they get a reward. Either their action is bad or good. And then they learn by doing, basically like humans learn, okay? By trial and error, okay? So, and this is the typical workflow of one of these algorithms that is called an actor-critic algorithm, where the agent takes an actions and takes feedback from the environment, that is the reward, gets some memory of its actions, then it updates its policy and retakes a step and so on and so forth. Where do neural networks come in here? Well, they come here as two types of neural networks. One basically calculates how what is the value of your state or your action, and the other one basically tells you with what probabilities you should take the next action. Okay, it's your policy. And this became quite popular when DeepMind basically was able to solve Go in this way. Okay, they were able to beat the world champion from South Korea in 5 games. There is a very nice 1.5-hour documentary of this. If you haven't seen it, it's really cool. Okay, and I will read it to this one because it basically repeats what I said before. This is from the webpage of DeepMind for the AlphaGo. We created AlphaGo, an AI system that combines deep neural networks with advanced search algorithms. One neural network, known as the policy network, selects the next move to play. The other neural network, the value network, predicts the winner of the game. Initially, we introduced AlphaGo to numerous amateur players of Go, so the system could learn how humans play the game. Then we instructed AlphaGo to play against different versions of itself, so it learns from itself. Okay? Each time learning from its mistakes, a method known as reinforcement learning. Over time, AlphaGo improved and became a better player. So in this documentary, you will see at some point when they play, I think, game 2, where the algorithm, the machine, makes a completely unexpected move that no human will ever do. That's move 37, okay? And then people just look at it and like, why did it make that move? And that move completely changes the game and gives the victory to the AI, okay? And at that point, they have this world champion saying, I thought AlphaGo was based on probability calculation and that it was merely a machine. But when I saw this move, I changed my mind. Surely AlphaGo is creative. Because people started studying now the way the algorithm was choosing strategies to learn how to play the game better. Okay, so that's really cool. So I have 2 examples here. We'll go a little fast on them. One is from mathematics, work by Sergei Gugov and collaborators. One game that you can play in mathematics is you have nodes, you want to untangle them. Okay, so that's a nice game. It fits in this pattern. So nodes are circles embedded in R3. You project them on a plane, they look like this, and there are allowed moves that you can do to untangle them. Now, a node may be an unknot. In other words, you can completely unknot it into a circle or not. Okay, so they wanted to use, they used reinforcement learning to basically see if such an algorithm can play this game and unknot the nodes. And this is an interesting game because it's also related to something known as the 4D Poincaré conjecture in mathematics. So what is the state space? The space of braid words. They can parameterize it using numbers. It's discrete. Action space, all these allowed moves and the relations that these nodes obey. Reward, and the negative length of the braid word. So basically, it's a negative number. It tries to maximize it, make it large, and take it towards 0, make it small. Okay, make a smaller length. So So RL significantly outperformed the random walker that selected random after all these moves from uniform distribution, and the rollouts identified sensible strategies. And in the later paper, they used related techniques to rule out over 800 potential counterexamples to the smooth 4D Poincare conjecture. So mathematicians can use it. So we might be able to use it as well, okay, if the task is appropriate. Now, another example that we did with Kostis Papageorgakis at Queen Mary is we wanted to see if we can use similar strategies to apply them on the conformal bootstrap program to understand non-perturbatively conformal field theories, which describe the generic high energy and low energy behavior of quantum field theories. And the conformal bootstrap fits in this previous logic that I mentioned in the amplitude bootstrap. You do not try to solve traditionally. In the 6D 2,0 theory, there's no traditional method to follow. So trying to understand what are sensible and consistent answers is the way to go here. But you have to deal with an infinite number of algebraic conditions for an infinite set of CFT data. You see, again, dimensionality is the problem. Okay? So, and in the series of papers, we initiated the program aiming to solve these conditions with machine learning methods, and reinforcement learning was one of the methods that we used. We also used algorithms from people working in NASA for optimization. We used all sorts of different things, and we were able to get interesting results that were very competitive with the standard semi-definite programming methods that people are commonly using in the Bootstrap community. And this is a program that is still ongoing that goes towards an alternative to standard conformal bootstrap methods, applicable in more general situations where, for example, positivity is not possible. So this is my epilogue. In 2 minutes, I will be done. So let me circle back to the beginning of my talk. Okay. So the link is reinforcement learning. Okay. What this paper, the DeepSeek paper, was mentioning is in abstract. What made it exceptional or very interesting was the fact that they were using reinforcement learning to induce reasoning. The large language model was not training by a lot of examples, which is the traditional method, which is called supervised fine-tuning. So you take a model, a foundational model, and the way you train it is you show it all of the internet, okay? That allows you to build a base model, and then you want this model to have specific capabilities. Be good at reasoning, be a good physicist, be a good astrophysicist, or whatever, okay? Then you have to do further fine-tuning, and this is also costly. So this is the step that DeepSeek was able to bypass. How? By using reinforcement learning, by allowing the large language model to spend a lot of time thinking and developing its own reasoning capabilities. So both DeepSeek R1 and OpenAI So1 models use reinforcement learning to increase their reasoning capabilities. Before answering a question, the LLM spends time to reflect on the answer, learning optimal reasoning strategies through trial and error. They have this moment here in the DeepSeek paper, which they say that it's an aha moment for the model during training. It's also an aha moment for them. What it does here is not very important. The point is that when you give it a question, it doesn't go for the response immediately, but it has an intermediate stage where it's generating text and basically trying things on its own. So here what it did is it starts solving this equation, then it stops and says, wait. There's an aha moment that I can flag here, and then it goes back, basically the way we also think when we solve a problem. We say, oh, okay, maybe we should go back and rethink that step. So the crucial, what they are flagging here is the fact that it went back to rethink the problem.
So that's different with ChatGPT.
ChatGPT is also doing that, but it's not open, so you don't know how they do it.
I've never noticed without giving a command that it goes back on its own.
No, this is happening, for example, this is happening internally. You won't see that. Okay. That's interesting. Okay, so the point here is that you're not hard coding everything, right? You're not hard coding, like all of these are features that are sort of emerging. Okay, this is really cool. So this is the last slide. So to summarize, recent developments in computer science are having a profound impact on scientific research. This is obvious. Okay. definitely in other fields. Theoretical physics is a latecomer to this game. More and more people are starting to think about this, and more papers come out in the archive. There are more and more groups that are basically trying to think about such problems. But I would hope, or I would like to argue, that it could be that theoretical physics, although it's a latecomer to this game, it might be an interesting playground for AI. Like, for example, Demis Hassabis, who is the co-founder of DeepMind, in this video in the beginning says, I think he comes from basically building games. And he says games are a very interesting context where AI can be developed. I think theoretical physics is also a very interesting concept where potentially AI could develop. For theoretical physicists like us, it could be an opportunity to think about traditionally hard problems in a novel, out-of-the-way box. Because you see, in all these cases I mentioned, it wasn't really the AI that was really solving the hard part of the problem. It was us bringing the problem in a stage where it could admit a particular approach. And that, I think, could be a lot of fun. Okay, so thank you.
Thank you very much, Vasily. Question?